then they notice, hey, Fred, you seem to be going away from me. What's happening? Neither one of us is moving. It's because their universe is getting bigger, as depicted by the expansion of this balloon. So if there were two ants, they move apart, even though neither one of them is moving through the space that they live in. Because some mechanism is inflating the balloon. This is as close as astrophysicists get to being able to talk in words about the expansion of the universe. The only reason we can use this, I don't know, analogy, metaphor, I don't know the difference. The only reason we can use this is we are viewing this expanding balloon from the third dimension, a dimension the ants are not aware of. So when astronomers talk about this stuff, they say, well, we are living on a sphere, and we can talk about it by writing equations in a fourth dimension, so that we have a three-dimensional object that is expanding. So once again, we can only use this technique to visualize what happens to ants on a balloon because we have the advantage of an additional dimension. So if that's a conversation, and you have to do this sometime at a university, it's amusing. If you're watching them interact, somebody's going to go to the blackboard and start writing equations of higher dimensional spheres. And then it gets really technical. But this does work, in a sense, to explain why we're receding from our neighbors. It's because everything's getting bigger. Now, here's a drawing. I have to show it to you two ways because of the way the artist created this. This shows the expansion rate of the universe. Right now, it's a certain value. In the recent past, the universe was expanding slower than it is now. And this number is lower than this number. And in the very early universe, it was higher than it is now. But this is backwards. You know, normally we say the past is, when you draw something, the past is on the left. So I've redrawn it like this. So all the words are backwards now. But you see, high expansion rate in the early universe, gradually slowing because the universe was getting bigger, the energy in the universe was getting diluted, so the expansion rate slowed, but then something happened right around here, 6 billion years ago. Or, yes, 6 billion years ago. Things started changing. So now I have to introduce you to what that is, what we think that is. And before I do, let me just check the time. We want to end on time. Let's go way back to the beginning. I showed you a drawing, and I said, this is, oh, sorry, too fast, too far. Oh, I didn't need to see. Oh, Lord, come on. Ah, okay. So remember I said back here where this shape was changing? That reflects the idea that not only is the universe expanding, but the rate of expansion is accelerating. So let's go back to the graph I was just showing you. Apologize again. Look away from this, maybe you will see something. Let's use this panel here. So what we think is going on here is there's something propelling the universe to expand faster than and overcoming the slowing of the universe getting bigger, the energy density of the universe going down. Something else is involved. And something else is pregnant pause. Dark energy. We don't know what it is. We don't know where it comes from. We don't know why it's so incredibly small. If you go in the lab and you try to measure the energy density, if you make a vacuum in a lab and you put probes in there and you study it all in every way you can, you get a number for how much energy is in a vacuum. And there is energy in an empty container that's there because of stuff we will talk about related to quantum mechanics. Quantum mechanics explains there can be energy in an empty space, but it can't be there long. It can rise and disappear. As long as it behaves within some constraints, energy can appear and disappear. It's happening in this room right now. Little infinitesimally small particles are being born and disappear, and everything is fine. You can observe that in the lab. If the measurement you make in the lab was applied to the universe and was a source of energy for expansion, the universe would have expanded so quickly that we wouldn't be here to observe it. The actual expansion rate we see in the universe is way, way smaller than we observe in the laboratory. No one knows why. But there's enough, this tiny energy is tiny. And the way it works is, if the universe expands, kind of starting to make a vacuum, dark energy will fill that vacuum and provide some energy. It expands more dark energy, and so it's kind of, it changed the trajectory of our universe. Instead of gradually slowing expansion, now we're in a part of the universe's age where the universe is not only expanding, the rate is accelerating.
And that began 6 billion years ago?
Yeah. And we can see that in the positioning of the galaxies. We can measure, we can determine their age by looking at their chemical composition using spectroscopy. We can look at how far away they are using Cepheid variables and other techniques. And I'll show you in a second. I'll show you the critical drawing. This is what led to the Nobel Prize. So for 60 years, from the time of Hubble until 2010 or 2005, people thought that the expansion rate must slow down because there's a limited amount of energy in the universe. Instead, we get this. Any galaxy, each of these dots represents a galaxy. Any galaxy appearing in the pink area is evidence that the universe expansion rate is slowing. Any dot that appears in the blue area says the expansion rate is accelerating. And virtually every one of the dots, every galaxy that was used in the study is in the acceleration side of the curve. You got a few, like you got this one, and this one, and this one. Out of, I think there are 31 galaxies that were studied. And so a Nobel Prize was awarded in 2011 for demonstrating that not only is the universe expanding, the rate of expansion is accelerating. In the far distant future, I actually have I'm going to say something now that I'll have a slide on later. And this is a good time to be interested in astrophysics and cosmology, because 5 billion years from now, the expansion rate that is underway now and will continue will have carried all the galaxies that we currently see will be receding from us faster than the speed of light. They will not be visible. And if you woke up one morning 5 billion years in the future and said, I'd like to be a cosmologist, the only stars you would see would be the stars in our Milky Way galaxy. The rest of the sky would be depleted because everything is moving away from us so fast that we can't see it. And you would have no way, starting from scratch, you would have no way to study the evolution of the universe. Everything we know about the evolution of the universe on a cosmological scale comes from the fact that we can see galaxies dating back to 10 billion years ago. But those galaxies will not exist for a future budding scientist. So if we want to give them our legacy, what we currently understand, you have to write it in a book that will survive 10 billion or 5 billion years. That could be hard.
And the Milky Way galaxy was formed about the same time?
Yeah.
It's the dark energy.
Well, dark energy's been in the game all the time.
causing the acceleration.
But we had to wait. If you were like a film director, you wanted to have a dramatic moment where the dark energy asserted itself, you'd have to wait for the universe to be of a particular age, and then the dark energy becomes dominant. In the very early universe, like the first billion years or so, dark energy was totally irrelevant. In fact, that intense light glow from the Big Bang, that became irrelevant. It's irrelevant now. All that's left is the cosmic microwave background, and if you put your hand out at night and hope that you're going to get warm from the cosmic microwave background, you're going to be disappointed because it's at 3 degrees above absolute zero. There's no warmth to be gathered. But it took billions of years before the dark energy asserted itself and now is dictating the expansion rate. And again, I assert, well, I'll show you a picture here. So they found acceleration. So, we got 10 minutes left. Okay, so we go in the lab. I already said this, but I want to repeat it. You go in the lab and you measure how much energy quantum mechanics predicts, or just make a vacuum and look for those little temporary particles that pop into existence and then disappear. You get a number. And it's something I teach my students at a local high school where I mentor the talented physical science students. And you can do that calculation. And you get a number. Then there's this, and the number is what this Dutch scientist Casimir predicted in the late 1940s. And people thought he was crazy, that an empty volume could have energy in it. And he was disregarded, but people decided to do experiments to see if he was right. And by the 1980s, they found, indeed, he is right. They actually measured the effect, the Casimir effect. And everybody was happy. There was joy everywhere. But there's just a teeny tiny issue. Just almost ignorable, but we always want to work it out, make sure we understand. And this minuscule little problem of that. That's the difference between what the Casimir effect predicts for vacuum energy and what we observe in the universe. 10 to the 120th. It's the worst calculation in the history of science. I have a picture of the scientist who, no one knows why the dark energy is so small, but I say again, if it wasn't small, dark energy would not have waited 6 billion years to assert itself. It would have been a significant factor right away, and everything would have flown apart so fast that our planet would not have existed. Atoms would just be isolated atoms, hundreds of millions of light years apart, and that's not a hospitable environment.
Question,
Yes, sir.
is the dark energy 10 to the 120th smaller than what was predicted or larger?
It's that much smaller. So the Casimir effect gives us a number, which has been verified in the lab. And the dark energy we see from the accelerating universe is 10 to the 120th times smaller. It's not a little bit, it's a dramatic. No. So we're getting near the end of today's event. I point out that Einstein is prominent on the cover of Time magazine, 1938, 1946, 1998, the accelerating universe. So I was a little off when I said 2005. 1998 was the Nobel, and people were seeing this acceleration in the expansion rate was a real thing. And then in 1999, he was declared the person of the century, not only for his science, but for his influence in dealing with nuclear weapons and a variety of other things. So we're almost out of time. I'm willing to stop here if people have questions. If not, we can go on a few more pages. You will eventually see all the slides. So no questions at this point? So let's see. Oh, so now let's talk about what we learned from the cosmic microwave background. So this is depicts a spacecraft that's going to measure the glow from the very early universe. And there's the glow. That's what it actually looks like. And the spacecraft measures that. And the space between the dark area and the red areas, the blue and the red, is measured by the spacecraft. And depending on the spacing of these hot and cold regions, we can get the geometry of the universe. So this if we had measured this, we would say, these terms are kind of vague, but the universe is open. That is, it has the geometry of a satellite. If we got this spacing between the dark and bright areas, we'd say the universe is flat. If we got this one, we'd say it's closed. And the data we have points very strongly towards flat. Like this. That is, if you look at, and let me tell you what these fluctuations are. So the microwave background is left over from the Big Bang, born 380,000 years after the Big Bang. If you point an instrument at the sky and you measure the temperature looks virtually the same everywhere. Now, of course, we're not looking at stars now. We're looking at the glow of the leftover from the Big Bang. It looks the same everywhere, but a detailed inspection shows there are variations on a scale of 1 part in 100,000. That's what these colors are coded to mean. So the coldest, the difference in temperature between the coldest and warmest spots in the background radiation is only a few parts per 100,000. Very hard to detect, and there's a Nobel Prize for making the first measurement of this from the ground, and 10 years later, another Nobel Prize for doing even better measurements from space. And right now, all the results show that the geometry of our universe is what we call flat. So let me illustrate flatness. Can I borrow this? I'm going to borrow the attendance sheet for a second. We'd all agree this is flat. Geometers point out that this is also flat. Because if I had drawn a triangle on this sheet before I rolled it up and calculated the total angle in the triangle, it's 180 degrees, and then I measure it after it's been curled up, it's all also 180 degrees. So there's a difference between geometry and shape. And we do not know the shape of our universe, but it's something related to this, bent in a circle to produce something called a torus, because ultimately, this is flat. And up until about 3 months ago, everybody was comfortable that our geometry is flat. And then some people, some smart people said, wait a minute, we've been looking at some data from one of the cosmic microwave background experiments, and we see a little bit of this. So there's another unresolved issue. What is the geometry of our universe? Here's where we were. The number 1 represents flatness. Here's where we were 2 or 3 years ago. That the universe is flat to a tiny, tiny difference. That's now in question. We don't know why. The mystery. Just like the Hubble constant. I mean, I have to, in this set of conversations, we have to talk about the truth about how confident we are. There's a saying, astrophysicists are frequently wrong, but never in doubt. But even now we have doubt. So, final thoughts. Yeah, so what this gets to, and there's a link here, is, remember I showed you that the universe was expanding faster in the past than it is now. We went through that dip right here. objects that were undergoing this expansion rate are now not visible to us. They've flown over the horizon. So now I have to tell you that the real, now this is the last thing I'll say today. The universe is about 13.7 billion years old. The most distant objects we can see are 13.7 billion light years away from us because they've been traveling that whole time. But there's a whole other group of objects